Hello, today I will present our work on embodied multisensory training for learning in children. Research on the embodied cognition and learning suggests that activity are facilitated when there is a body engagement and multimodal stimulation. And the use of body can be a mediator of mathematical knowledge, and this has been studied starting from the 80s. There are several works indicating that even simple gestures can have a positive impact on mathematical learning. There are also recent findings suggesting that audio feedback associated with body movement can be crucial during the development for learning of new spatial concepts. Within the Withdraw project, we investigated how this sensory motor link can be used for learning. Here we present a new approach based on embodied learning with the audio and visual feedback that can be used to improve angle and fractions after some multisensory trainings that are based on human-computer interaction. We use an interdisciplinary approach in which we put together pedagogical knowledge with neuroscientific information, and we did a user-centered design to validate and develop the technology. At the pedagogical level, we conducted a questionnaire with more than 200 teachers of mathematics, and 75 of them agreed that the mathematical concept that we addressed, fractions and angles, are concepts that are very difficult to be understood through the visual modality. At the neuroscientific level, we measure perceptual correspondences between audio pitch and angles aperture during the development. And we demonstrated that audio-visual size correspondences can be used for learning and can be useful for improvement, discrimination of different angle aperture. Starting from these pedagogical and neuroscientific inputs, we developed two training activities. The first one is the robot angle activity. In this activity, the child has to open the hands in order to reproduce specific angles. The angles to reproduce as to create the figure of the house. In this case, she's reproducing this angle here, and through a Kinect, it is possible to record line the end movements. When the angle aperture is correct, it is given a feedback in green, suggesting that it has been recognized. So in the body fraction activity, we use the body as an image representing an idea representing the fraction. The numerator was represented by the distance between the ends and the denominator between the foots. The fraction number line was in the middle of the body. So the child has to match to create a specific fraction by creating an association between the denominator with the legs and the numerator with the hands. Again, it was recorded through a Kinect, and it was represented here by this figure, the proportion between the aperture of the hands and of the legs. In order to validate our technology, we tested 24 children of 7. Half of them were 7-year-old, and the other half 9 year of age, from the Italian primary school. We divided the group in two subgroups. A group who was trained with the robot angle activity, and the other group with the body fraction activity. So this is the methodology we use. In session 1, a part of the session 2, we we did the pre-test and the post-test at the end. And in session 2, 3, and 4, there were three moments of training with the two activities. During the training, we increased the complexity of the training So at the beginning, it was during the robot angle and body fraction. The task was to reproduce very simple fractions and angles, and then the complexity increases. As I said before, we had the feedback associated with the correct response. So it was a visual feedback, green light when the body, the response was correct, and a red light when it was not. In the case of the red light, the child has to reproduce again the task until when he didn't reach the green light. We tested the pre and post evaluation test. For this, we use three main tasks. The first one is a measure of number estimation, in which the child has to put in a line from 0 to 100 a specific number, for example, 80. In the second one, we did a measure of proportional reasoning. In this case, the child has to match a specific proportion indicated by this amount with one of the two presented on the right. In the third task was a measure of general visual spatial abilities. So the child has to match a specific figure composed by different sub-elements with the ones below. These are the results. For what concerns the positive number line, we didn't observe any significant difference in the delta. The delta is considered as the difference between the pre and post test, and a positive delta suggests improvement. We observe, on the other hand, a significant improvement considering the age. Indeed, the post-hoc analysis suggests that there was an improvement significantly different from 0 at 7 years of age, in the group of 7 years of age, but not 9. The same tendency was evident in the negative number line. So there was a difference for the 7 and the 9-year-old, even if it was not significant. No difference was observed for what concerned the different activities. So then the results of the proportional reasoning, also in this case, we observed an age-dependent difference. So we did not observe any improvement in general, but in the group of 9 years of age, we found an improvement for the body fraction and not for the robot angle. So it seems that also in this case, there was an improvement depending on age. Finally, for the visual spatial geometry task, in this case, again, we did not observe any difference in improvement in general, but we observed a difference from, with respect to 0, for the 9-year-old group in the robot angle and no activity, other activity, but not for the body fraction. So these results suggest that 7-year-old children improve their performance in the number line task with both training activities, and the 9-year-old children enhance their performance in geometrical tasks after the training with the robot angle. The proportional reasoning task, indeed, produced an effect only for the 9-year-old children in the fraction activity. So this result may be related to the school level and the learning stage that these different age groups have. Indeed, it seems that the training in the improvement is associated with different ages, and the training can be different for different ages. And in particular, the 9-year-old may benefit most from the training in the proportional reasoning and fraction understanding, because they already have some basis to learn this specific concept. In order to let more children using this kind of activity, we have developed an app. We have done a platform optimization, and we have developed an app to be used by children in the classroom at the elementary schools. And this activity has been developed with the use of the interactive whiteboard that is already in place in most classrooms without using any other complex systems such as Kinect and PC. And this is available for free online at this link. So to conclude, learning experience mediated by body engagement seems to have a very strong potential to support learning. And in this work, we tested whether a multisensory activity requiring students to use their body to reproduce angles and fractions through the association between visual auditory feedback can improve the comprehension of this concept. So the training results suggest that audio and visual feedback associated with body movement is indeed informative for spatial learning. And overall, these results suggest that there is a crucial role on sensory motor association for spatial processing during the development. Thank you.